a few quick questions after each talk, just so you know. And before we let the speakers take their stages, please allow me to briefly introduce them. Our first speaker is going to be Professor Simon Tindemans. He's currently an assistant professor with the Department of Electrical Sustainable Energy at the Delft University of Technology in the Netherlands. His research focuses on statistical risk management for power systems. He has a specific research interest in the control of the aggregate power consumption of heterogeneous and unpredictable resources, and he's an IEEE member. Our second speaker is going to be Professor Xiaojie Wang, who is currently an assistant professor in the Department of Electrical and Computer Engineering at McGill University in Montreal, Canada. And her research interests are in the general areas of power system stability and control, UQ in power system security and stability, and wide area measurement system-based detection, estimation, and control. She's an IEEE senior member and serving on the editorial boards of IEEE Transactions on Power Systems, Power Engineering Letters, and IET Generation, Transmission, and Distribution. And our third and last speaker from academia will be Professor Sairaj Dople, who is currently an associate professor in the Department of Electrical and Computer Engineering at the University of Minnesota in Minneapolis in the US. His research interests include modeling, analysis, and control of power electronics and power systems with a focus on renewable integration. He's a senior member of IEEE and serving as associate editor for the IEEE Transactions on Energy Conversion and the Transactions on Power Systems. And our speaker from industry is going to be Dr. Miao Fan, who is currently a senior software engineer at Siemens Industry in Schenectady, New York. His research interest area is in power system reliability analysis, uncertainty analysis, dynamic modeling, and renewable energy integration. He's a senior member of IEEE. And without further ado, let's get started with our technical presentations. Our first speaker is Professor Simon Tindemans. And now, Simon, the floor is yours.
Thank you, Mert. Thanks for the introduction, and yeah, happy to finally be in a meeting with this panel, and yeah, happy to see where this goes. But let me now introduce a few of the things I've been working on in recent years. Now, I have to apologize. My laptop is in for maintenance, so I'm doing this on my iPad, and I hope this all works. So bear with me. Here we go. Okay. So hopefully you should now. 1, 2, 3. Up. You should now see my screen. Does this work?
Yes, we see your screen, Simon.
Fantastic. Okay, great. So let me start. I have about 20 minutes. I'll give you a quick overview, and it has to be brief, so I can't go into all mathematical details, but of two very closely related bits of research that I've been involved in. And the overarching theme here is statistical estimation of uncertainties in power system adequacy studies. So let me start with the context here, right? We're looking at resource adequacy assessment. So, right, this is about the ability to quantify the ability of a power system to supply all demand and to essentially calculate security of supply risks, usually in some numerical form, such as loss of load estimation or expected energy not supplied, and so on. And the context here, why is this important? I mean, it's always been important, but why is it particularly important now is because we see an increase in security supply risks, or at least perceived risks, due to the increasing uptake of renewables and essentially a worsening investment climate for controllable generation. And therefore, in a number of regions, we now see capacity markets being created, which essentially translates into a lot of money being put on the table on the basis of such adequacy assessments. So that kind of gives an urgency to this kind of questions. And at a very high level, the process that's followed in all these studies is 2 or 3 steps. Sometimes the third is not there. First is you define a probabilistic model. So that's also part, I see, of the task force goals, but that's not part of my talk here. So I'm going to assume that some probabilistic model exists. Then having such a model for, let's say, future performance of a power system, we will assess its statistical properties, so the delivery risks in this case. And then third, we will investigate factors that could reduce risks, such as which reinforcements should you make and how much value do you assign for additional capacity, how much capacity should you purchase on a capacity market auction, etc. Now for this second and also for the third step, usually, and not in all, there are exceptions, but in many cases, people resort to Monte Carlo methods, Monte Carlo sampling methods, to assess the statistical properties of the probabilistic model. And when you do so, it's always essential to quantify the sampling uncertainty, right? And typically, you don't have enough time for anything but the simplest academic models. You won't have enough computational power or time to sample this thing to death. So at some point, you need to stop and then quantify your sampling uncertainty. And in this talk, I'll be briefly sketching two different aspects of this, where uncertainty quantification is technically a bit challenging and also leads to very interesting bits of research, if I say so myself. So let's go number 1. And this is, you can find the paper right there. This is about estimating risks from small samples. And the motivating case here, and that's just one out of many, is you see a case on the left. I made some randomized network just to have something well controlled with 1,000 nodes, many lines, and I'm going to do some cascading outage analysis. Now, I don't go into the details of the model here, but what matters is there's many possible of such outages, and here I'm just looking, for example, at all cascading outages that result from a 3-line outage. Right, so you take 3 random lines out and then see what happens. And then sometimes the network continues operating just fine, and sometimes it doesn't. And in fact, when we do this analysis in this particular model, then sampling here 10,000 out of all this huge number of possible combinations, we end up sampling only a tiny fraction. And then on the right here, we can show the fraction of power not supplied as a result of those. And ultimately, only 0.5% of these sampled combinations leads to any outage at all, right? So any power not being supplied to the customers. So we have a potentially huge problem where we sample only a very small subset, and of that very small subset, only very few samples show any interesting behavior. So therefore, we're dealing with a rare event analysis. So in this case, if we put those numbers in, we get this expected power not supplied, of this fraction. That's a fraction of the total power in the system, right? So that's a fairly small number. But can we trust that result, right? It's sensitive to sampling errors, and have we actually observed the worst case? So that was the motivation for, well, a very long and deep rabbit hole that I disappeared into. And again, I'm not sketching the actual steps. I'm just telling you the outcome that we arrived at after a lot of work. And it's this method that I'll just sketch to you in a minute that, well, I've named Bayesian interval sampling. And the idea here is that, this method is characterized with the 3 keywords here. It's Bayesian, so it accurately quantifies the state of knowledge, starting from some prior knowledge, going to updating that with the data we have. It's non-parametric, so it doesn't impose any particular class of distributions, and it's robust, with some little stars on it. You have to define what robust is, but it's generally robust. So within certain constraints that you can set, it's even in the most ill-behaved cases, this method works well. Works well to do what? To estimate what the underlying distribution could be, right? So what we'd like to do is to combine all this knowledge, and in this case, it is both, it's both regular probabilities and imprecise probabilities that I'll show in a minute, to describe the state of knowledge that we have regarding this distribution and the distribution of these outages in the, the actual network, even though we sampled only a small subset. And you can have an efficient computational implementation of this framework. So very briefly, this is an example that I'll show you just to see how this works. Here we have a fairly well-behaved distribution, 0,1 log normal distribution, from which we sample, in this case, only a very small number, 15 observations. And those 15 observations are the little red lines over here, right? So on this axis from that distribution, here's what we sample, the little red dots over there. And then, of course, in our application, we no longer have this distribution, and we try to recover it from the data as best as we can. Unfortunately, we have only 15 points. So what do we know? Our next step is that turns out that one way to look at this is to say, actually, these 15 points define 16 intervals. They define 16 intervals between the measured points. And then what we do, and again, this is a bit of magic if you don't follow the steps, but you essentially say, aha, each of these intervals, we assign a random probability mass. That's our Bayesian posterior distribution, where we assign this weight to each of these masses. And of course, you see there that the points that are close together, you get a large amount of probability mass close together. And where the measurements are further spread out, you get less. And my statement here, and proofs are in the paper, not here, is that that accurately describes the state of knowledge of this distribution, of this cumulative distribution function. So, okay, what does that mean? Now, let me just take you through those results. So first is, what it means is we can now generate these distributions by sampling from this Dirichlet distribution and putting random weights on there. So now I've done that 5 times here, right? So again, taking those 15 original data points, those are the little red lines over there, and the green bars are, the height of the green bars is the amount of weight that I put on that interval. So what we have here is we generate a distribution over distributions. And one way to describe that, and again, this is going to be short, unfortunately, but it's a really interesting kind of field here. We can describe that by a probability box, because what we've done here, this probability box, this diagram over here, is assigning a certain amount of probability weight to each interval, but we don't actually say where in the interval that probability sits. It could be smoothly distributed. It could also be placed at one point. It could be on its left boundary or on its right boundary. We don't know. And in fact, we don't actually necessarily care too much. So that's what this probability box gives you. For this assignment of weights, the green bars on top, you can draw a cumulative distribution function that is in the bottom here. And you see that that is partially undetermined, right? So it has the right weight in each of the intervals, but it doesn't actually specify where. So this gray area is basically, this probability box contains all possible cumulative functions that fall inside any of these boxes. So they could be smooth and they could be step functions, could be discrete, continuous, whichever, we don't say. So here you see a little video, and I hope this plays over the over Zoom, but there you actually see a number of random draws that we made. Again, same example, the 15 points. So here's our possible inferences for what this generating function could be. And there, the dotted line is the actual function that generated the data. So here you see that you have some kind of posterior view on what that distribution might have been. Okay, all very nice. How do we use it? Well, the way we use it is as follows. And let's now say that, for example, I want to calculate the mean, right? Which is what I did in the first example of the cascading outages, the expected power not served. So I want to calculate that on the basis of such samples. So I start with my measurements, generate a whole bunch of different distributions by drawing these random weights. And then for each of these, what I can do is, if you look at this single probability box function over here, what you can do is you can take essentially a best case and a worst case. And this works for a very, very large class of risk measures. And actually, most of the ones we're interested in, like the mean, you can either hug the top of the line, the curve, or the bottom, right? Where the bottom is the highest numbers and the top corresponds to the lowest numbers. So for each one of these random draws, you can generate a low estimate of this quantity and a high estimate, and a low and a high. And therefore you get, essentially you start drawing potential, you start drawing two curves here, and you can then plot the CDFs, right? The cumulative distributions of both these guys, or your pessimists, or actually optimists in case of outages, or your optimist estimates and all your pessimist estimates. And you get these two curves. And that tells you essentially you get two distributions of outcomes, and they correspond to the upper and lower bounds of all the intervals. And you don't have actually any more information on what's inside these intervals. So this is now a hybrid form of uncertainty. It has both probabilistic elements, these curves, and it has the gap between it, which is non-probabilistic. And what you can do here is you can then, within those curves, get a 90% credible interval. But you have to combine somehow the 90% credible interval of the red curve and the blue curve. And you can just take the most extreme cases to take the conservative scenario and then arrive at a robust, credible interval for this mean in this case. All right, so doing that, you have this is kind of a step-by-step recipe for getting a robust, maximally robust result. And what's nice here is you can see this actually works, right? So here's where I've drawn 50 numbers from a 0 to 1 log normal distribution that was truncated, right? So it has some fairly, the occasional quite extreme result, and we sample only a small number. And what's shown here is, okay, try to now estimate the mean, where the true mean is 1.65, using the mean and a confidence interval on the mean, I should say, 95% confidence interval or credible interval, using three methods. One is the typical kind of student T or normal distribution. Second one is percentile bootstrap, and the third one is this Bayesian interval sampling. And here you see the coverage probability if we repeat this very, very often, right? So how often, which percentage of the cases, if we do this 10,000 times, this experiment, does our 95% confidence interval actually contain the true mean? And we see that for this first two methods, this is actually quite a bit lower, and that's a well-known well-known behavior. These are not very robust metrics. Even worse, if we create this kind of ill-behaved distribution at the bottom, where we put 1% of the weight onto the most extreme boundary, and we assume that we know that this boundary exists and that we know it, these other two, they really plummet. And again, this Bayesian interval sampling remains, maintains a good coverage.
I'm not sure, but we cannot hear you anymore. Is it me or?
No.
Hi, Simon. I cannot hear you as well.
Yeah, I can
Same
hear
problem
everything.
here.
Hi, Simon. We lost your voice. Hello, Simon. Can you hear us?
Looks like his computer just froze or something.
Okay. So we should like wait. I think we can wait like 1 more minute. If Simon is not coming back, so we can move to next guest speaker, and after that one we can let Simon finish. How do you think, Mert?
Yeah, I think that's it.
Yeah, while you are waiting, actually, let me say a few things. Because I did some work actually on risk assessment of cascading failure leading to blackouts. The big issue here is the tail of the distribution. We should not sample all the say, so we need to concentrate on the tail, and that's why we are using important sampling and this kind of thing. Because if you sample all the space with extremely small number of samples, well, you miss the point. The mean does not reflect extreme events. You have to concentrate on the tail of the distribution. That's all what I said. This is Lamin. Thank you.
Okay, thank you, Dr. Mili. So Simon is rejoining in the meeting. Hi, Simon.
Hi, sorry, can you hear me now?
Yes, yes.
Okay, I'm very, very sorry for that. Let me just share the screen and then wrap up, because otherwise I'm taking too much time. Apologies for that. So somehow my connection got dropped. Here we go. There has to be a first and a last time for trying all things, and this is probably the last for trying this. I hope you can see this now again.
Yes, we can see it.
Yes, okay, perfect. Yeah. All right. So the idea here is that what you're doing is you're trying to estimate risks, and in nearly all cases, there are exceptions if you look carefully, but all the general risk metrics that you try to calculate are expectations. So what you're trying to do is to calculate the expectation of some kind of impact function, that's what I call H, as a function of the additional load added to equal this baseline risk. And just moving that risk over to the left, you see that you're trying to find the 0 point of some stochastic equation. And that is the stochastic root finding problem. Now, and again, that's what you do here. And then the trick here, and I won't go into how we go about this, but the trick here is then, of course, the challenge becomes that you're trying to find where this line here, is the risk difference crosses 0. And if you want to do this in a proper way, maintaining this, well, this uncertainty quantification, right? So you're trying to accurately quantify, well, what is the ALCC and you do this in a sample-based manner, it is not so easy to do so in a way that that actually gives you accurate error estimates in this direction, right? So you can easily kind of sample one point and get error estimates in this direction. That's the usual Monte Carlo procedure. But what we're trying to do here is trying to find the zero crossing and then give errors estimates in this direction. That's not easy. There's a few ways that I will show. I'll just breeze through that don't work as well as you might hope. Bisection doesn't work. Stochastic approximation works, but doesn't actually give you the confidence intervals you need. And then there's a third method which we've looked into, which is the probabilistic bisection method. That is actually quite neat and does seem to work. And with that, I'll give you some, I'll skip this one because we're out of time, but essentially, just to show you on the right, this works, and it even works for some pretty complicated cases where we're trying to calculate the capacity value of interconnection. So this is a multidimensional quantity, and that also applies there. So with that, let me just summarize the main points here. First is that resource adequacy studies often require Monte Carlo methods. If you use Monte Carlo methods, it's essential to carefully assess sampling noise. And I've shown two examples, one on rare event analysis, where if the events become really, really rare and your distributions are sufficiently ill-behaved, many standard methods break down, and we have this Bayesian interval sampling idea that seems to solve those issues at the cost of being quite conservative. Second is if you're calculating capacity values, this is a stochastic root finding problem, and naive approaches there don't work very well at all. But luckily there are some advances that seem to be, that seem to help a bit, but we're still working on this. So with that, let me wrap up, go back and stop sharing. And happy to take questions.
Hi, Simon. So
yep.
When you are disconnected, Professor Lamimidi asked you a question regarding the real events. So he's saying that for this kind of real events, typically people estimate making the tail behaviors, like using importance sampling. So, but you are mentioning you are estimating the mean. Dr. Midi thinks the mean might not be very meaningful for the real events on the tails.
Okay. I think there are two differences here. Yes, it's true that I think you would still, in many cases, even if you have rare events, you would still be interested in knowing the mean, because that's the typical risk metrics, for example, that are calculated or estimated are means, are expected, energy not supplied or loss of load expectation. They are the mean. But it's true that there's a very, very large majority of essentially zero measurements in there, right? So in this case, 99.5% of those cases, and often more, is actually zero. So yes, you would use importance sampling. Now, if you use, if you use subset sampling, then you can immediately apply this technique. If you use importance sampling, that is less easy. It can still be done because essentially you're taking measurements of, you're essentially calculating the mean of weight times value, right? And you can apply the same method that way. The only problem is that it becomes harder to bound the result because it's difficult to exclude the possibility that weights can be very, very large. And that can actually cause some issues here. I hope that more or less answers that question.
Yeah, okay, thanks, Simon. I think one of the advantages of your method is you can give a bound. So you say this is based on the 95% of confidence interval, right? But within the interval, you mean it is not probabilistic.
So you could generate more. I mean, so these two curves that I showed, right? So there's this kind of the blue and the red curve at some point. there is there's more information in there, so you can also present those. I should mention two things. One is, one of the inputs is some kind of bounding of sorts on what can happen, which could be infinity, but then that, well, for measures like the mean, that's not very nice. But then you can just report those curves, and there's more information there than just an interval. So there is a bit more, but there are limits to what you can know, and there's kind of this fundamental. But that's what I like about the method on a conceptual level. It clearly specifies what you can know from what you've seen and what's unknowable because you haven't seen enough. So there are these two types of uncertainty that are really numerical and non-numerical.
Okay, thank you. So anyone else?
I think we can move on to our next presentation in the interest of time.
Perfect. All right. Thanks so much.
Thanks, Simon. It was a great talk. Thank you very much.
You're welcome.
Xiaojie, are you ready to share your screen?
Yes, sure.